This is a tutorial about the Dhall configuration language. I'm going to describe what that language is from the point of view of functional programming. This is the official website of the Dhall language. And the main point that they're telling you about is that it is a templating language for producing JSON or YAML output, like this, for example. And that's a valid point. So this is perhaps a very good usage for this language. Dhall is a very powerful language that is at the same time very small. It will take a very short time to learn it. And it will solve all the problems with templating, all this string-based interpolation. It just all goes away because the Dhall language gives you at the same time a template and a type or a schema for the data. So you can describe what the schema is, and then you can create values of that type and export that type to JSON or to YAML. So then you'll create automatically correct YAML, automatically correct JSON. The type will be checked. You cannot possibly forget values, cannot possibly mix up strings and numbers and so on. So this is a very valid usage of Dhall, which you can explore and use in real life. Now I'm going to talk about another usage of Dhall, which is to learn functional programming, to learn advanced idioms of functional programming. From the point of view of functional programming, YAML is a purely functional language. Sorry, not YAML, Dhall is a purely functional language that has very few features, and yet those features are sufficient to implement most patterns of functional programming. Anything you have heard about, functors, monads, applicatives, traversables, recursive types, and type classes, all that can be implemented. So at the same time, Dhall is a little simple. It's on the simpler side. It does not have a lot of features, so it will not take a long time to learn. It also has features that help you learn functional programming. And I'll talk about this. So first of all, what is Dhall from the point of view of functional programming? It's just a language where you can define functions, types, and values. There are a few built-in types, like natural. Other than that, you just define functions or values. A Dhall program is a single value. The let construction is similar to defining a variable with some value, and then you say in, and then you can use whatever you have defined in an expression. You can see that functions are applied to arguments without parentheses. Like this is a function that's applied to argument 10. And the result is another function that's applied to this expression. And that expression in turn is a function ID that is applied to the argument natural and then applied also to another argument 20. So the ID is defined like this. So this is a function definition. Lambda is keyword similar to def or function or something like that in other languages. And this will be familiar if you're familiar with Haskell. And then these symbols are not necessary to type. You can type ASCII symbols instead, but this is nice to look at. So now notice that in this language, there is no difference between type parameters and value parameters. They can be mixed in any order. Usually you would first define type parameters, and then you would define value parameters, because you might want to use the type parameter in a definition of your type later. So obviously first you have to define the type parameter. But this is just in this case. So you could have, for example, a function that takes, let me show you an example. You can have a function that, so I'm going to type lambda like this, that takes a value parameter, that returns a function that takes a type parameter, which is defined like that. And then it returns, let's say, a record that has, or let's say you take another value parameter of type A, and then you return a record where you have, for example, number is X and value is Y, right? Now, if you look at the type, which is inferred for this function, it is a function that takes a natural number, then it takes a type, then it takes a value of that type, and then it returns a record of which you have two fields. The number must be of type natural, and the value must be of type A, whatever that A was in here. Then you can use that function to create such records. For example, F123. Then I have to say what type that is. Let's say I have say I type text, and then I need to give a value of type text, which is just a string. And the result is going to be a record with number 123 and value ABC. So this is an illustration of how Dhall works. So you can have functions with parameters. Parameters can be types, parameters can be values, and you can use the type that you have previously as a parameter to define types of further parameters. And you can also use values to define types of further parameters, which means that essentially you can have dependent types, types that depend on values. Now, this is an advanced feature that Dhall does not support very well. It is to be used very occasionally. At the same time, this makes Dhall simpler because you can just learn this one construction. This is a type for all X natural, for all A type, for all Y A. You just have one construction for types and values and everything. To define a function, you do this. You have a lambda. So for example, what is f? F is this lambda that we just defined. And to define types of these functions, you use the forall symbol, which you can type as like this, forall. But you can also type the Unicode. So this is an illustration of the Dhall syntax. So the typical function application is written like this. Functions are curried. So they take multiple parameters in this way. You can have records as well and other types. So this language doesn't have any other constructions. You can have functions and values, and that's it. You can apply functions to values. You can define new functions. There's nothing else you can do. There are no effects. There are no printing functions or reading files, writing files or something like this. There's nothing other than computing a value. So this kind of resets your mind towards purely functional programming and towards looking at what types everything has and do the types match and so on. Because all the types have to be specified explicitly, it is a little verbose. So this is an identity function. An identity function needs to be written like this currently in Dhall with a type parameter written explicitly, whereas in most languages, that type would be inferred by the compiler for you. Now, this is certainly something that makes Dhall more verbose. At the same time, I found that it helps when you're learning these concepts. It helps to see where all the type parameters are. What are they? What would the compiler have to infer in a language like Scala and Haskell? Learning this is valuable. Typing this extra thing is a small annoyance that, in my view, is okay. It might be changed in later versions of Dhall so that there is some type inference, but the design of Dhall is that it should be very straightforward and there shouldn't be any magic features. Another important feature of Dhall is guaranteed termination. So because there are no effects, there is no recursion. So you cannot define X if X is already, you cannot define X using X itself in its definition. So recursion is simply not available. You can code recursive functions in different ways, but not all recursive functions, but only those that are guaranteed to terminate. So you can, for example, write a loop. If you wanted to write a loop, you need to know in advance how many times it will be repeated. So for example, let's define a function that adds 10 to a given natural number. Okay. Let's check that it works. So that's going to be 133. And let's apply this function 100 times to some number. So to do that, we use a built-in function called natural fold, which says you apply 100 times to a function, sorry, to a value of type natural. You apply a certain function to, let's say, initial value 1000. Let's if we add uh, uh, the number 10 100 times to 1000, we should expect 2000, right? So that's what it does. So you can write a loop. Essentially, this is a loop that applies this function 100 times to the result and it keeps applying it. So first you get initial value, then 1010, 1020, 1030, and so on. So after 100 repetitions of this, you get this value. But the number of repetitions need to be specified in advance. You cannot write a while loop where you keep repeating until some condition first becomes true. That is not possible in Dhall because it cannot be guaranteed that that loop would terminate. And Dhall wants to guarantee termination. So this termination guarantee is very strong. So it constrains the language, it constrains your code. And this is a good thing for a configuration language, but it is also a good thing in general. You would like that your program terminates. You would like that it's actually impossible to write a program that does not terminate, that enters an infinite loop. It is impossible in Dhall to write an infinite loop. There's no program that Dhall would accept that writes an infinite loop. That is a very interesting feature. For example, a program that in Haskell or in Scala would generate an infinite loop would be just something like that, right? So you say there's a natural value loop and it's equal to itself plus one, right? You can write this in Haskell, you can write this in Scala using lazy or using a function. And once you try to evaluate this value, this loop, then the program will never stop. In Dhall, this is not allowed because this variable here is used in a definition of this variable, but this variable is not yet defined. So Dhall does not allow you to do that. So if you want to define something, then you write equals, and then on the right-hand side, there must be everything that's defined. So everything on the right-hand side must be defined. So you cannot use recursion like this. Identifiers in Dhall can be pretty much anything. That's a very interesting feature where you can have an identifier in backticks, and that can be any string. I actually used this in some places where instead of a name, I just write a descriptive phrase that says what it is. Like this function will print blah 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 in under such conditions. You can just write this phrase as a name of that function, and then you call that function. That makes code self-documenting. That's a nice feature. So primitive types are natural and integer. There are also some other types, but they are not, they're opaque. They cannot work with them. Like there's a double type, but like this, you can have a value of type double, but there's nothing you can do with it other than print. You can convert it to text. So then you get text 123, but that's all you can do. There's nothing else. You cannot add two of these values. Notice this is an identifier. So slash is not a special operator because there's no division built in Dhall, and there's no subtraction. I mean, subtraction you can subtract natural numbers, but you have to write it like this. And there's no minus. So minus is just a character that doesn't do anything. You can use minus in names. You can just use slash and minus in names because of this feature. Dhall has product types, which are records with names, and Dhall has coproduct types, which are unions with constructor names. It's a very interesting feature how Dhall implements the union types, because in order to create a value of a union type, you need to say X. You need to say that if that value is in this part of the union type or in this part of the union type. So you say it's an X of 1 to 3, for example. But X is an undefined function. So Dhall requires you to put an entire union type here with a dot syntax. It's like a record with a dot syntax, but in a union type, the dot syntax is required to get the constructor. And this feature means union types are structural. So you can have different union types that have the same names, X and Y, but different types here. And there's no confusion because you always have to write the entire union type here dot X. Now, of course, in real life, you don't have to always keep writing this everywhere. You can put a name to that. So say you can assign types to variables. Types and values are very similar. You can have types as arguments of functions. You can have types as values that you assign. So you can just say this is like a type alias, and then you can use that type alias as if it were a defined type. But there's no special syntax for it. It's just a let, like any other variable. And then you say my type1 dot x, and that will give you this part of the union type. So records and union types, they're structural. There's no nominal typing. So, for example, record, like this record, doesn't itself have a name. It's the same as this one because the order is unimportant. So you can say this is this type record one, but this is just a type alias. It is not the name of the type. There's no concept of a name of a type like in languages like Scala or Haskell, where you define a name for the type separately from defining that type, or together with defining the type. But you could define the same record type with different names in Scala and Haskell, but you cannot define it in Dhall. So this is a unique type, and you can assign record one, record two. It's the same thing. So record one and record two are actually the same type in this code. And you can see that if you write a value x and a value y, they're exactly the same type, and you can use them interchangeably. So this is a structural typing. It's a very interesting feature which simplifies the language. There's no this concept of type name or scope for that name. This is a value, literal type value that you can just copy, and it's completely unique. And so that simplifies kind of the thinking. So I found it very illuminating to write programs where you don't have type names, like in most other languages. Pattern matching. So there's pattern matching for union types. In Dhall, pattern matching is a little different in syntax. It's exactly the same in semantics as in all functional languages. You have a value of a union type and you want to pattern match. So you want to provide functions that map this data into some result, that map this data into some result, and that map this data into some result. So you have to provide three functions. In Haskell, you would write this kind of syntax, case of. In Scala, you would write a match expression with, again, functions that you have to specify. In Dhall, you specify them in this way: as a record with record names corresponding to the names of the union type constructors and the explicit functions that you just write here. There's no special syntax. These are just functions. So this actually is just a record, which is a value. You can create that value separately and put it into the merge expression. So merge is like match or case in Scala and in Haskell. There's an optional type, which is built in. It has a sum and none, so it's like Scala-like names for option. There is very little else. There's list type. List type is built in. For example, this is a list syntax. The type of this is list natural. So list is a type constructor. What is a type of list? It is a function from type to type. And now you see that Dhall has hierarchy types. It has functions from type to type, and therefore you can have a type that is like this, and therefore you can have function parameters that are of this type. So this is a kind of a consequence of the design of Dhall. It's because types and values are kind of on the same footing. The only difference between types and values is that a value has type, and you can write something like this, right? So the value 123 has type natural. Type natural cannot be used in this way. That would not type check. The type natural has itself a type that is called kind. Sorry, it's called type. Type has a type that's called kind, and kind has a type that's called sort. and sort doesn't have a type. So this is a kind of an advanced feature here that I'm illustrating, but I'm illustrating that pretty much everything has a type. Types also themselves have types. Types of types also have types. So types of types is kind. But kind is a strange thing that you cannot do very much with. You can have a arbitrary kind, for example, would be like this. Type, type, type. That's a kind. So you can have parameters of this type if you want. But it's very little use to write something like for all x kind. Now, what would that x be? Well, how would you use that x in your program? So x could be this, or it could be just type, and you cannot use x as a type annotation necessarily. So you don't know what to do with this x really. There's not much use of this. And because there is not much use of these very abstract types of types, I find it very good that Dhall cuts it off at sort. So sort is a symbol that you cannot really use in Dhall. Like if you say sort, it's an error. It's actually a type error to write this symbol in Dhall in most places because it itself doesn't have a type. So Dhall kind of stops this infinite descent into what's called type universes. So if you learned about complicated dependently typed languages like Agda and Idris and Kok, then you will know that those languages have infinitely many type universes. So, for example, 1 to 3 is of type natural, natural is of type type, type is of type kind, kind is of type sort. This is in Dhall, so, right, this works. But in those languages, this descent is never finished. So there is type 1, type 2, type 3, type 4, type 5 forever. Now, I find that this is an unnecessary complication for most practical purposes. It is certainly a complication that was due to the specific design of those languages. But Dhall has a very interesting decision where you just say, you stop this infinite hierarchy of type universes after the third universe. So I found that you can write pretty much every functional idiom without those universes. And Dhall gives you a specific example of how to do that. So I find it a very interesting solution to this inconvenience of having infinitely many type universes. Now, type constructors you can define. There are functions from type to type. And here's an example. Let me copy this. So int is a type constructor that takes, it's a function that takes a type and returns another type. And we can create values of type, for example, int text. How do we do that? So that will be a value that has a record. The first element of a record is some text. The second element is again some text. And the third element must be integer, let's say 10, right? So this is a value. And let me check that this value type checks with type int text. Yes. Right, so it would not type check with, say, int double. Because actually it is text that needs to be there. So this is the type that we can create now, like a type constructor. And you see, this is a function that takes a type as an argument. the syntax is just the same as syntax for applying functions to arguments. So this is a Haskell-like syntax, and it's applies to everything. And so this is why I said that this language is simple to learn. The syntax is simple to learn. There are, of course, many things here that are not obvious and require learning, but the syntax is simple. You just have a function and you apply functions to values, and that's it. Or you can apply functions to types. You can have functions as values, function types. You can have function types. You can have all kinds of things that functional programmers want. And I found it very important that a language used for schemas, JSON schemas and so on, has all those features. And you don't have to use them, but having those features is very liberating. It means that you can have refactoring of your configuration through functions with very flexible types. You can have type constructors. For example, you can have a record that depends on a type, so that certain parts of the record have fixed types and other parts of the record have variable types, and you can put that type in there, and Dhall will check that your record actually has that type. Union types mean that you can model very flexible problem domains. Optional type means that you can model values that are missing, possibly missing. Function types means that functions can be used as arguments of other functions. That's an extremely powerful design pattern that replaces half of the object-oriented design patterns just by itself. Curried functions and functions with type parameters I just illustrated. And here's an identity function that depends on a type parameter, a value x, and it returns x. So there are some syntax conveniences. For example, you can say let multiple times before saying in. Rather than saying let something in, let something in, let something in, just write it like this. And that's okay. Well, I will skip other features. I'll talk a little bit about modules, and this is also a very interesting solution of how to make an extremely simple and yet good enough module system. So probably I don't know enough about module systems to make a judgment, but to me it looks like a very nice solution. And the solution is that values can be imported from external resources. Here's an illustration. There's a value input list, which is imported from a file. And the file, let's say we create this file with this name containing this Dhall expression, which is a list of integers, natural numbers, to be precise. So this code inputs that expression from that file into the variable called input list. And this code imports code from the web. Now, if you go there and look at this, what is that? It's Dhall code. Now, that code will by itself import sum.dhall from the local relative path, so from the same directory. So let's see where that is. Right. So this is the sum. So this is Dhall code for computing a sum of a list of natural numbers. And there are some unit tests. So I did not talk about this feature yet, but this is a useful feature where you can write unit tests inside your code. Um, so this is how you can import values, Dhall values, from external resources. So what's an external resource? It can be a file on the local file system. It can be a URL, and there are some features to provide headers for this HTTP call in case you need authentication. And finally, it can import values from environment variables using this syntax. So these are the three types of external resources that Dhall can import from. And that is all it can do. Now, there are no other ways of importing values from other places. So you cannot read from keyboards. Using this feature, you can create a module system. One Dhall file must be one expression, one Dhall expression. So one value. Each expression will be evaluated, and then you can import that into another file. So using that, you can have modules because expressions can be records. So you can have a record. You can, for example, write code like this, where you define a few things. You define maybe types and values, and define some function, how to print usernames or whatever. And you have an expression, which is a record. Now, this is a shorthand for saying it's a record with name, username, and the value equal to the same. So the result is that this can be imported into a record, and then you can use that record to take parts of it and use in a different Dhall program. So that is like saying I'm importing a function or a type from a different module. And this module exports these values. There's no need to say exports, public, private. There's no such thing in Dhall. Everything is just a single value, and all values are public. So if you want to have something private, just don't export it. Don't put it into this value. You can have let here. So for example, this test and validate, these are private values. They are not exported. They are going to be evaluated, type checked. So for example, there's some validation that needs to be imported. Fine, that will be done. This will be checked, but those values won't be exported. So this is like making them private. So in this way, you can export values from one program to another, reuse values, make libraries where you export a bunch of things. So Prelude is a standard library that exports a bunch of functions and types. You can see the documentation here. And for example, here are the exported files, and you can look at this. So for example, this identity function is in the standard library. Function composition is in the standard library. And in this way, you make modules. So just by the feature of importing a value from another file. So this is conceptually very simple. One file is one value. Where that value is doesn't matter. It can be just a big environment variable, or a file in the local file system, or a result of calling some HTTP server. And that server doesn't have to serve files, of course. It can just be a server that serves response, dynamically computed, for example. So I will skip this hashing feature. This is interesting, but that's not what I'm that I'm going to talk about. Um, Let me talk about the assert functionality, because this is another thing that helped me learn about dependent types. Um, and perhaps I will just finish the tutorial at that point and leave you to read my tutorial later if you feel like. So what are equality types? Dhall has this syntax. Now, this syntax with triple equals sign creates a type. This type is, in a sense, a function of two values, x and 123. Now, x is actually defined here also to be 123, the string 123. So this type is essentially, it's the type 123, triple equals 123. So this expression by itself is a type. It's not a value, it's a type. So there are values of this type. Now, what are those values of this type? Now, there isn't any representation specifically for those values. The intention behind making such a type is that this is a statement or a proposition that we would like to prove to be true. And the proof of this proposition is a value of this type. That is the idea behind making types like this. To represent the value, this type, there's a syntax in Dhall which is assert. So if I say assert, that gives me a value. So I can say, for example, proof 123, right? So I defined now proof 123 as a value of that type. Now, this is a bit strange, maybe, but this is actually the expression that proves that this string 123 is equal to itself. If I write a different type, for example, 123 equals 456, that's another type. And at this point, nothing is wrong. This is just a type. So I can say let bad equal type is that. So, okay, well, bad equality type is defined. But I will not be able to define any values of that type. If I say assert, that's going to be a failure. And that's a type error. So this says that this expression doesn't have the right type. So in other words, this cannot be satisfied. So there is no proof that they're equal, and you cannot construct a proof. So assert tries to construct this proof and fails. And this failure is at type checking time. So this is not a runtime failure. This needs to be at type checking time. So that's a little complicated to explain, but I just want to say that to make sure that you understand. This is not a runtime check that these are equal. This is a check that happens at type checking time. And if any of this fails, then the rest of the program isn't going to be evaluated and nothing is going to run. So let me say that the equality types are used in Dhall mostly for unit tests. So, for example, if I want to check that this function add 10 actually works as expected, right? So then I say assert add 10 1000 must be equal to 1010, and that passes. Or in my program somewhere, I could write let underscore in some other expression. let's say true. So that will be equal to true. And this thing is ignored in a sense because I'm not using it, but it is checked. So if I make it wrong, then this will not work. So in this way, you could see what I just showed you also for the natural sum. They define the function that adds natural numbers, and then there are some tests for it. So that asserts that the sum of this list is 10, and the sum of an empty list is 0. And these assertions are checked. So if you import this URL, then it means that this has been checked. So in this way, you can assure that your function does what you want using unit tests. There are also other things that you can do with equality types. So let me show you how that works. Actually, I have it somewhere here. Yeah. So there's something called Leibniz equality types, which is a very complicated type of this kind. And however, this type reproduces the entire functionality of the equality types of this triple equals. So in some sense, the triple equals in Dhall is just syntax sugar for this sort of type. And certainly it's a good thing to have because it would be very difficult to write this all the time. However, it's important to understand that this is essentially just syntax sugar. It doesn't have to be there. It doesn't have to be built in. It could be just implemented using the features we already have. So let me explain how this works. So this type is a function that takes a type. It takes two values of that type, A and B. They're of type T. Then it takes an arbitrary function, which is like this. This function takes a value of type T and returns a type. Unknown type, arbitrary function that can take the value of type T and return any type that you want. And then, given that function, you need to produce a function from type FA to type FB. Because F produces types out of values. FA is a type, and FB is another type. So you're supposed to be able to produce a function from this type to this type, given A and B. So why is this expression an equality type? Because it is not possible to implement any values of this type unless A and B are equal. So if A and B are equal, then FA and FB is going to be the same expression. And then this function from FA to FB is just going to be an identity function, which you can always implement for any type. So you don't care what function f that is, you just put an identity in here and you're done. But if A and B are not equal, then FA and FB are two completely unknown different types because you don't know what f is. F is one of your arguments. So FA could be natural and FB could be Boolean or text or whatever. You don't even know what that is. And you're supposed to write this code that works at the same time in the same way for all f. And that's impossible because you don't know what those types are. So you cannot write a function from one unknown type to another different unknown type. You cannot do that. So because of this trick, this Leibniz equal, after applying it to a type and to two values, gives you a type which only has values when A and B are equal. And then you can create a value, which is usually called REFL of that type. So here's an example. If you apply this Leibniz to natural type here, and then you have two natural numbers. So this is a type that looks like this, and this is a type that looks like this. Now, you can implement values of this type. It's like that. It's just an identity function that takes an arbitrary value of type F0 and returns, again, the same value. But you cannot implement any values of type Leibniz equality natural 0, 1. So that is impossible. REFL is the way to implement that Leibniz equal T for equal arguments in general. So it tells you that this is possible. And that is the basis, the foundation of all the proof assistance and dependently typed proof assistance, where you have this type, which is equality type, and you provide evidence that two values are equal by providing a value of the equality type. So using that, you can reproduce the assert feature. You can just create values of assert type out of a value of the Leibniz type. So if you have a value of type Leibniz txy, you can create a value of this type. And then you can also use that at type level to constrain that two types are equal using a similar code like this. However, Dhall does not implement that. So for the equality of types, Dhall does not implement the assert syntax. No matter, we can still do it using this Leibniz equality, and we can do more about that. We can actually provide reasoning. So for example, if you have a value of this type, then you can get a value of this type. Translated into the language of proof, it means that if you have evidence or you have proved that x equals y, then you can also have proved that y equals x. And there are further such things like transitivity. If x equals y and y equals z, you can prove that x equals z. And if x equals y, then for any function f, the values fx and fy are equal, you can prove those things. So the good thing is that you can prove them by writing the code so I show it here. I won't go through this right now, but you can write code that converts a value of this type into a value of this type. And that code is the proof. So in this way, you have a completely assured reasoning, a reasoning that is proved and machine checked. This is the foundation of proof assistance. Now, this is a little complicated to reason about, but looking at Dhall helped me understand it, because in Dhall, you have to write out every parameter, every type parameter, and when you apply a function, you have to write down all the types that it is applied with, and that kind of helps you understand what's really going on. There is no magic. They're just values and types, and you're just applying one thing to another, and that's it. And so this is a very interesting experience for me to go through this. So I wrote it down because I thought it was a very interesting educational tool. A very simple language, which does not really help you to prove anything complicated, but it gives you an understanding of the basics. So then once you understand this, you can go on to more complicated dependently typed languages more easily. Let me just finish this tutorial by an explanation of these things. So dependent types and the universal quantifier versus the lambda symbol. Because I found that this is perhaps confusing. And again, it was confusing to me until I had to deal with Dhall and understand how Dhall is done. Um, this repository, by the way, is the Scala implementation of Dhall. It's not particularly performant, it's not fast, it's slow and takes too much memory, but it is a kind of proof of concept implementation that helped me understand how this is working, how to implement such a language, and this was very educational. So what is the difference between the universal type quantifier and the function symbol? The main difference is that the function symbol lambda defines a function value, a function as a value, whereas this symbol defines a function as a type. So the type of a function. Now, type of a function is not the same as the value, right? It's just like type natural is not the same as the number 10. So if you have a function, for example, this one, it takes a text value and appends ... to the text. So this is a function of type that can be written like this. So type of that function is for all x of type text, we return a value of type text. So you see, this is a type. So this is not a value, and this is a value. So this value can be applied to a text. So let me write that code. Right, so x dot dot dot. Now, if I say f ABC, the result is ABC dot dot dot. So I can apply f to a string. What is the type of f? Type of f is this. I can assign some variable to that type, like this. So type of f now is a type, and this type of f is equal to this. But type of f is not a function. I cannot apply type of f to something. Error, not a function. So type of f is not a function. So it's like I would say 1, 2, 3 ABC. That's not a function. Or I would say natural ABC. That's not a function. Natural is a type. You cannot apply that to some argument. It's not a function. And so this expression is not a function. So expressions that are created using the universal quantifier, the forall symbol, are not functions. They're types. Or they're always types. They're not functions. Expressions that are created using lambdas are functions. They're not types. So this is the difference. And this kind of thing is a little confusing because you say, well, for all, why can't I say this is also for all x? I am computing this string for all strings x, aren't I? Yes, I am. But this is not a type. This is the actual function that computes it, and the type of that function is this. So you can talk about that using words for all. That's not precise enough. Precise would be to say, this is a function that takes an argument of type text and returns the string. This is a type of a function. This is a type of a function that takes an argument of type text and returns a string, returns a text. So that is the difference, and you need to keep this in mind because you can mix and match lambdas and foralls, but only in a certain way. For example, this is incorrect for all x and then lambda, because this is not a type. For all x, there must be a type, because you're saying this is a function type. Once you start writing for all, the result must be a type. And you say, okay, this is a type of functions that take x and then return a value of what type? Of this? This is not a type. And this is therefore wrong. But in the opposite order, like this, it is correct, because it says it's a function that takes x and returns a type. That's fine. A function can return a type in Dhall. A function can return a value, it can return a type, it can return a kind or whatever. That's fine. But this itself is not a type. The type of this function is for all x type. Let me put that into Dhall. Right. So this type of that is for all x type, return type, because this is a type. So this is a function whose type is written like this. This kind of thing takes some time to get used to and to get right, to understand. But essentially, it's a very basic distinction that helps understanding what for all means. It's a type. And what lambda means. It's a value. It's a function value. The same thing happens in all programming languages, in functional programming languages, in Scala and Haskell, and all the other programming languages. You also always have this distinction between function values and function types. Some languages don't have the for all symbol or the lambda symbol, but they all have this distinction, because all functional languages must support the idea of a type of a function. So functions have types, and you should be able to write down what that type is, because you want to say that some function takes another function as argument, and you should be able to say what type of that function it takes as an argument. And so all functional languages must have some kind of syntax that corresponds to this distinction between lambda and for all. And seeing this quite explicitly, that you have to write it every time in Dhall, really helped me to clear up my mind about those things. And I will finish this tutorial by talking about dependent types in Dhall. So what are dependent types? They're types that depend on values. That is what it means. So they're depending on values. Those types that depend on types are type constructors, like list and option and optional and so on. They are type constructors. They're not dependent types. So types that depend on values. So what do you mean it depends on values? It means that for each value, you return a different type. Here is an example. You take a value, Boolean, and if this Boolean is true, then you return natural as a type. And in Dhall, you can just write that. You can return a type from a function. Or you return text. Now, this is a little artificial, this example, but actually it could be useful in some ways, because you could you could use this as a function that checks that certain values are correct. How do you do that? Well, for example, you write functions like this, where you say, well, this y is an argument of type fx. And so depending on X, this could be a different type. And your program should supply arguments of the right type. I have an example here of using this kind of trick where I implement a safe division function, a function where you divide one natural number by another, but you are not able to divide by 0. And the way of implementing that is to first have a function that is of dependent type. It takes a natural number, and if it is 0, then it returns an empty type. This is the empty type, or rather void type in Dhall, and this is a unit type in Dhall. So if y is 0, then this type is void. It has no values, or else it has a unit type, and the unit type has a single value, which is written like this. It's an empty record. So now, if we have a division function that's unsafe, we can make it safe by adding one more argument, which is going to be of type non-zero y. So let's say you have a division function that I implemented before using a loop. As I was indicating, loops must have explicit number of repetitions, so that's fine with, I'm not going to discuss this in this tutorial anymore, but this function, it takes an argument x, an argument y, and then it takes an evidence argument of type non-zero y. And this argument can be given only when this type is unit and not void, because there are no values of the void type. And so if y is non-zero, then indeed you can call this function. And if y is 0, you won't be able to call this function. Now you can provide the evidence that y is non-zero by just giving this value. And if you write things like this, that's fine. And this would be a type error because this type does not fit the value. The type must be void, but this value is of type unit. And you wouldn't be able to call this function with the second argument equal to 0. And so this constraint is enforced at compile time, so to speak, at type checking time. The price is this extra argument that you have to keep writing in all these functions. But this is essentially, again, so this language helps you to understand all this hidden magic behind other more sophisticated, more advanced languages. So I even find that this is illuminating, that you have to write all this by hand to look at all these types and to see how that all works. So let me finish this tutorial by saying that I'm writing different examples of how Dhall can implement different things like type classes and higher order function programming and floating point even I implemented, or numerical algorithms, just that you have to know how many times to repeat your loops in advance. But that's essentially okay. All the type classes that functional programming uses, like different kinds of functors and monoids and so on, and even how you can do inheritance of type classes. Now, I talked about equality types. Then for recursion, there are certain other tricks for encoding recursion in this type of language where you don't actually have support for recursion built in, so you cannot write a recursive type like a tree immediately, explicitly, because a tree is a union type, which is either a leaf or a pair of branches, and each of the branches is again a tree. So you're not allowed to do that in Dhall because you cannot define a type tree using itself. So for that, there is a church encoding, so-called, which I explained here at length. And there are techniques for working with church encoding that are not trivial and need to be explained. For example, how to do pattern matching on such a tree, and how to compute its size, and how to pretty print it, or write algorithms on trees. I go on to other such things, and how to convert recursive code to this kind of language where you don't have built-in recursion. And I'm going to explore how to derive type class instances automatically from previously given instances for different type classes, and so on. So essentially, this language is, although it's telling you that this is a programmable configuration language, JSON plus functions plus types plus imports, but there's a lot in types in this language, which makes it so powerful that it can actually implement pretty much all the idioms of functional programming, even down to checking the laws in some cases using assert. For example, checking the laws of monoids or something like this. And this is just because the author of this language chose to use the functional paradigm with types and functions rather than any other paradigm that other templating languages are using. So while I agree that this language is perhaps best used for configuration management, to me, this is a very exciting vehicle for learning functional programming and for understanding more deeply why is it that functional programming is so powerful? What makes it so powerful? Let me finish with one remark. Most non-functional programming languages, C, C++, Java, Golang, Python, and so on, most of those languages, even if they have types, do not provide you function types. Well, Python nowadays does provide you function types, but it's a kind of an add-on. They don't provide you union types. Python, again, does in some way as an add-on. Doesn't work always very well. It's not designed for that. So languages that like C, C++, Java, the old style languages, Golang is the same, that don't have union types and don't have function types, they cripple the programmer. That is the lesson of functional programming today. And that's the lesson that I realized that can be formulated like this. You need union types and function types. In other words, you need, in your programming language, you need to be able to write that this function has this type as a function, or this argument is a function of this type. Or this argument is a union of these types. If you can write this, then so much is open, so much power is open to that language that you don't need a lot of features. You can just implement equality types and law checking and all kinds of type class derivation. You can implement that in that language just because you have union types and function types. Actually, union types can be implemented via function types and the universal quantifier. The universal quantifier, which is this forall, which is necessary if you want to have function types, because that's what it does. Now this forall, once you make it flexible and apply it to everything, like I just showed you, It allows you to implement Leibniz equality, church encoding, so you can implement recursion, you can implement union types, you can even implement records if you didn't have them. It's so powerful to have function types and the universal quantifier, which comes with function types. So it's a pity that today's languages don't give you that functionality. And Dhall shows you how much you can do given very few features, and just given just given that feature, the function types and the universal quantifier. So let me finish the tutorial here.